Hey, hi, welcome back, and this is going to be part 3 of the review for the chapter test. What we're going to do here now is do a problem. And as we're going to do this problem, I'm going to ask you to do it with me. You can pause or stop the video at each step of the way and see how well you do at finding the information. We're going to assume that we have some very high desk, all right? And we're going to make this desk 2 meters high. That's a pretty high table. And this is going to be our floor. Well, let me see. It was a little unsteady there, so let me see if I can make that a little bit better. All right. And we're going to have a baseball up here rolling, and the baseball's rolling in this direction. And it's got some velocity, v, which is simply in the x direction. So right now, what do you call this? This, you should know by now that you call this horizontal projectile motion, because the ball initially, right here at this point, right over here, when it just leaves the top of this big tall desk, this point, the ball only has a horizontal component to its velocity. The ball is not going upward or down, it's simply going straight out horizontally initially. So it's called horizontal projectile motion. So the ball is going to follow a path that's going to look like a parabola, because we got classic projectile motion here, and it's going to land some point away from the table. And I'm going to tell you that the distance here where it lands is going to be 8 meters. So it lands right there, 8 meters away from the table. Now the first question I'm going to ask you, question number 1, is how long is it airborne? Or let's just say, instead of saying airborne, let's say in flight. I like better. This is not very useful. How long is it in the air? Let's say in the air. So I'm looking for time. Now, you could stop and think about, how would you solve this problem? How would I find out how long it's going to be in the air? In other words, from the time it leaves the desk or the table till the time it hits the floor, how many seconds is that going to take? Okay, so we're back, and we're going to talk about how to solve for time. Well, in order to solve for time, I'm going to consider the vertical motion. The vertical motion. And for the vertical motion, I'm talking about the y direction. And I know that the displacement in the y direction is equal to the initial velocity in the y direction times the time, plus 1/2 the acceleration in the y direction times the time squared. Do we know the displacement or the change in position in the y direction from the initial to the final? Of course we do. It was up 2 meters high, the floor is at the bottom. The ball dropped down vertically 2 meters. So we're going to put -2 for our change in y position. Because we use the minus because it fell downward 2 meters. What's the initial velocity in the y direction? The initial velocity is the initial velocity in the y direction now, because we're talking about vertical. Okay, so let's only concentrate on vertical. Over here, right here at this position here, just as it's leaving, it has no vertical speed, no vertical velocity. So this initially is 0 times time plus 1/2 the acceleration. Now, what's the acceleration in the vertical direction? Well, it's due to gravity, and you should all know by now it's negative 9.8 meters per second squared, and then t squared. So 0 times time is still 0. This will set up to -2. Half of negative 9.8 is negative 4 0.9 and then t squared. So t squared is going to be 2 divided by 4.9, and then t is going to be the square root of that, 2 over 4.9, which is going to be equal to, I calculated 0.6, well, let's say 0.64 seconds. In these videos, I'm not being concerned with significant figures. I think that's important, but it's more important right now to get the concepts down and not worry about the number crunching so much. I want you to understand what we're doing as far as how to solve these things, and we worry about significant figures later on. But so let's just call it 0.64 seconds for time. Assume that there's 2 significant figures. So there we go. That's the first part of the problem. Now the next part of the problem may ask, what do we ask in the next part of the problem? Next part of the problem, we wanted to know what was the initial velocity of the tennis ball or the baseball as it left the desk. So part 2, what is v sub x? That's the initial velocity. That's initial velocity. In this case, the initial velocity only has one component, so it's v sub x. How do we figure that out? I'll let you stop this video and go and see what you can do with it, and then come back and we'll work it. All right, so what you should have done was, remember, we'll consider the horizontal motion now. Horizontal. The horizontal direction. For horizontal, we talk about x, and we have delta x is equal to the initial velocity, and that's why I always put sub I to tell you it's initial velocity in the x direction. That is not times, that's just the sub x times the time. Now we don't have this here because there is no acceleration in the x direction. In fact, the reason why the velocity in the x direction stays constant is because there's no acceleration in the x direction. So our formula is simply that the delta x, which means the displacement in the x direction, the change in its position in the x direction, is going to be the initial velocity in the x direction times the time. Well, what is this delta x? Can you all tell me what that is? Well, if this is my x-axis here, and this is like my y-axis here, then from this point to this point, all right, this is my delta x. That's the distance it traveled. We know that that's 8. That 8 is going to be equal to initial velocity in the x direction times the time. Well, what's the time? We calculated the time right here. So let's put that in, 0.64. And so we've got 8 is equal to velocity in the x times 0.64. So we can solve for the velocity in the x by saying velocity in the x is 8 divided by 0.64. And if we do that, we get velocity in the x is 12.5 meters per second. So that's the velocity in the x direction. Now one final thing we need to do, and I'm going to do this one in yellow, and let's see where would be a good place to put it. I guess I have to put it down here. Let's say 3. What is the final velocity, v? Well, first of all, can we identify where is the velocity going to be final? It's going to be final right here when the ball hits the ground. What is the speed which it hits the ground? Well, if we look up here, the final velocity v is going to be some vector coming in at some angle hitting the ground. That vector v is going to be composed of 2 components. A velocity here in the x direction and a final velocity here, v in the y direction. So I got to look at the x component and the y component when it hits the ground, and if I have these two, then I could find v by using the Pythagorean theorem and the inverse tangent function. So let's do that. We know what Vx is, we just solved for it, and we know with projectile motion, whether it's horizontal or non-horizontal, doesn't matter, velocity in the x direction should stay the same. So velocity in the x direction has already been done for us, it's 12.5. All we need is the velocity in the y direction right here when it hits the ground. Well, how can we do that? The final velocity is always equal to the initial velocity plus the acceleration times the time. Now, if I'm talking about the y direction, I would simply keep in mind that I'm talking about the y direction, so I make all of my velocities with respect to y. Final velocity in the y direction is the initial velocity in the y direction, which is what? The initial velocity in the y direction is, well, here's the initial position right here. Right there, that's my initial spot. So what's my initial velocity right there in the y direction vertically? 0. Has no initial vertical velocity. It's all in the x direction. So the initial velocity in the y direction is 0. That's initial. Plus, what's my acceleration in the y direction? That's going to be negative 9.8 meters per second squared, as always. And now what is time? Time is how long the ball is in the air. That's what we first calculated in step 1, and that was 0.64 seconds. So you see that the final velocity in the y direction is going to be equal negative 9.8 times 0.64, and I'm getting negative 6.3 meters per second for the v in the y final. So now all I need to do is draw this for myself. Here's my x component, which we know is 12.5. My x component stays the same through the trip. My y component is 6.3. Negative means it's downward, so I'm just going to draw it down and put 6.3. My total velocity is going to be the combination of those two. I'm going to put it here as v. It's going to be the combination of the x component plus the y component. And that v then is going to be the square root of the 12.5 squared plus the 6.3 squared. And if we do that, I believe I come up with close to, let's say, approximately 14 meters per second for v. Almost done. We just need this little angle over here. That little angle in there. Well, theta will be the inverse tangent of the opposite side, which is going to be the 6.3, over the adjacent side, which is 12.5. And if you do that on your calculator in degree mode, did I do that right? I did it. I guess I didn't. I guess I did that. I guess I did that wrong in my notes here. So let me just redo it. Inverse tangent of 6.3 divided by 12.5. That's 26.7 degrees. So this is 26.7 degrees. Because we want this velocity in the y. Yep, that's right. We want the opposite over the adjacent for the tangent of this angle. So that's my bearing. This is my magnitude. This is my final velocity and magnitude. This is the angle that it's coming down on. So I hope that helps. Study that problem. It's real important to know all these steps, and you could back it up and practice it a couple of times.